Okay, so we are learning lift today. You want to know how lift is created. Okay, so we know that this is an airfoil. This is the airflow over the airfoil and under the airfoil. We say that lift is created because of Bernoulli's principle and Newton's third law. We are focusing on Bernoulli's principle here.
Killer, murder.
Murderer.
So violent.
Violent guy. Girls, listen to it. Violent, which means good and bad. So, this airflow is going on top and it's going faster. We say that all the time. This is going slower. Faster means lower pressure. Slower means higher pressure. High pressure is going to push, go towards low pressure, create a lift force in that direction.
One question.
Go.
Yeah. The airflow on top is an obstacle. The airflow below, there's no obstacle.
Yeah.
Why is it going slower than the top?
That's what I'm getting into. Yeah. I'm going to
Should
explain
be
why.
opposite way, right?
I'm going to explain why this is going faster. That was the question that we were stuck at, right? We want to know why this goes faster, why this goes slower. Now, the common myth everywhere on the internet, and you might have heard this from your instructors, 99% of them would say that this goes faster because this airflow, or imagine these air molecules, they have to travel longer distance on top and lesser distance or shorter distance at the bottom surface. So they will go faster to reach there. But my question here is, who is telling these molecules here that the distance is longer? They don't know about it. So how do they know that they have to go faster? They cannot know. It is not possible for these molecules to know that they have a longer distance ahead of them.
Mm-hmm.
So they cannot go faster because of that reason. The reason why they go faster is because of Bernoulli's principle, which normally is not taught correctly. And it is not taught in the detail that we are going to get into today. Okay, so we know that Bernoulli's principle is nothing but what the guy did. A very, very good friend of mine from high school, Mr. Bernoulli. I don't know his first name, but I just remember his last name. I hope that's his last name. But he did an experiment in a venture, right? It looks like 24 inches waist of a beautiful girl, but this is actually a venturi tube. We have an airflow or any fluid that goes in. As it travels or as it gets to this area here, which is squeezed, kind of like, you know, there's less air or less space here, so this air is kind of squeezed in here. We say that this starts to go faster here. And then as it goes out of this area and goes back here, it gets its same speed as it was here. Right? So we are saying that here we have faster velocity of air, which will lower the pressure in this area, and comparatively we have a higher pressure here, right? That's what we know as Bernoulli's principle. Increase in speed results in a lower pressure, or vice versa, lower pressure increases speed. Same thing is happening here, exact same thing is happening here, but the reason why it speeds up is because of this. So to understand this, you have to know this first. Air is, you cannot compress air at normal atmospheric pressure. There is no way for us to compress the air in this room. If you want to compress air, you need to seal it in a container. That means there has to be a sealing around it. There has to be, like in the oxygen bottles, I don't know if you know this, but the bottles, the thickness of that wall is this thick, and it's made of lead, which is a very heavy metal. So to compress air, we need a really strong sealing or a really strong container if you want to compress air. Now here, there's nothing here. So how do we compress this air? That happens because of an invisible sealing.
Yes.
Yes. because of an invisible ceiling, which is because of, so I'm going to draw that ceiling here. So this is created by the air pressure from top. This is basically nothing but the air pressure, right? So if I move my hand, imagine this, if I move my hand like this, am I disturbing the air on top? I'm not disturbing the air on top at all. I'm just disturbing this air right here, right? Same thing's happening here. As this air molecules, as these air molecules, they start to go up this airfoil, because of the ceiling on top, see what happens. They are all nicely spaced, happy in this area, but as they get here, they are cramped. Does that make sense? The only reason why they are cramped is because there is an airfoil here, there is a ceiling here, there is a surface here stopping it from flowing in this same flow, and on top there is air pressure, which is hundreds of pounds. Basically anything above you, you are at 5,000, so all the air above 5,000 is pushing down on you.
The invisible ceiling, is it because we know that Earth have different layer on top of it?
What layers?
Like
Troposphere and all that?
right.
No, it's not because of that. It's just air pressure. No matter which layer you are in, doesn't matter. Imagine Earth. Here's a beautiful planet Earth. Love living here. If aliens from outer space are listening to this on their YouTube channel, Earth is awesome. Love living there. It's green, blue, white clouds, beautiful women from some parts. Some are not as good.
It's full of racist people.
No, he's kidding. Go Trump! Okay, so this on Earth, if you take a column of air here, right? Now air we know goes miles up, right? From the surface here, it goes miles up until we reach space, right? And that boundary is decided by what?
Stratosphere.
No. The boundary where there is no air anymore, that is called space, outer space, right? But how do we know where is that, or what decides? Now, not on every planet this column of air will be of the same length. On Earth, that thing is decided by a term called gravity. Gravitational pull, because of our planet Earth, it's pulling everything down. Apple falls from a tree because of gravity. So, this gravity force, this is pulling everything down, including the air molecules. So, close to the Earth's surface, you have more air molecules. Hence, though we have high pressure. As we go up, we still have air, but just that the density decreases because the pull of Earth decreases. Correct? So, what I'm getting here is that this ceiling is created by all of this. So, let's say that you were here at this altitude. All of this air is, all of that weight of all of those molecules above you is the force on top of you, which is nothing but the air pressure at that altitude. We know at surface standard pressure 29092 or 1013.2 or 3 hectopascals, millibars. As we go up 18,000 feet, it becomes half of that from here. And as we go higher and higher and higher, it keeps on decreasing until you reach outer space and there is no air pressure. Correct? So what I'm getting to here is that if you understand this, then this will make sense, that this ceiling is nothing but everything on top of you, all the air molecules on top of you applying air pressure, creating a very, very strong ceiling. Because of that, the air is, we are trying to compress the air, but we know that air is not compressible at normal atmospheric pressure. So instead of being compressed, it's going to squeeze the molecules together, which in terms or indirectly or in other words is compressing it. Correct? So that's what happens here. Now this is what happens. These molecules, the reason why they start going faster, we understand why it's compressed here now, or why it's squished together. But why do they run faster? That's because we know that each one of these air molecules has static and dynamic energy, right? The potential and the kinetic energies. You know those, right? Potential is something which it has but it's not using yet. Kinetic is it's moving. So these are moving here. Moving. So it has static and dynamic both. Gets here. Now, because of this air flowing this way, which I didn't draw, but here we go now. Because of all of these molecules going this way, once this kind of space tightens up, these molecules cannot go back. They cannot go back because this air or this is pushing them. These molecules are saying, hey, move, keep moving. And these guys are saying, hey, there is not enough space here. What do? We're just cramped like in a train in Bombay. Right? Have you traveled? You have been to Mumbai? You go to train there, the general class, you will be squished. I love it if they're all girls around me, but if they're guys, I just don't like it anymore. But that's what these guys are telling these guys. These guys are saying, hey, keep moving. But these guys say, not enough space. How do we move? So what they do is they push them now. They're like, you are not going to move, we're going to push you. They just push them. So simply enough, these guys are going to start flowing faster. They will start flowing faster because they have no control anymore over their speed. The guys behind them are pushing them. That explains why air flows faster. It has nothing to do with more distance here, less here. So it has to travel faster to reach there. None of that stuff. If you want to understand this with a daily life example, imagine a hose. You water plants in the garden. You have a hose. You run the tap. Okay, you have water coming with some pressure. Same thing as this air coming with some pressure, some force in some direction. Now if you squeeze on that hose, the water is going to go further out, right? Now when you squeeze, the water doesn't know how far to go or how fast to go. It doesn't know. Same like these molecules don't know how far they need to go or how fast they need to go. All they know is they are being squeezed in this small space. Same like when you press on that, or when you squeeze, or when you try to limit the space through which the water is going, the water molecules have no choice but to move faster because they cannot go back. Why? Because there is some water coming through with some pressure which is asking him to keep moving. Hey, keep moving. So they have no other choice but to move faster. So they start moving faster. They move faster. That creates lower pressure. Comparatively, here you're not going to get that low pressure because there is no ceiling here. Right? There is no ceiling. The pressure is always from top, never from the bottom, because the gravity pulls everything down, doesn't throw them up. So higher pressure does the magic force of lift. Nailed it.